In this video, we're going to start Chapter 17. And Chapter 17 is on electrochemistry. And electrochemistry is the interconversion between chemical and electrical energy. So using a spontaneous chemical equation to create electric current, or using electric current to drive a non-spontaneous chemical reaction. So it's involved with the interconversion, so converting between the two, of chemical and electrical energy. The device that this occurs in is called an electrochemical cell. So a battery is an example of an electrochemical cell. So the device that this interconversion occurs in. And there's two main types of electrochemical cells. One where our chemical reaction is creating electric current, another one where the electric current is driving our chemical reaction. So the two are opposite of each other. So two main types. A galvanic cell, also called a voltaic cell, if you've heard of that term before. I'm going to use galvanic. So this is the one where we have a spontaneous. So something, remember, spontaneous means the reaction is going to occur on its own without any sort of outside influence. So I have a chemical reaction that occurs, right? A spontaneous chemical reaction. Sorry about that. Generates an electric current. And if you've had physics before, just remember an electric current is just the flow of electrons. And we'll talk in quite a bit of detail about galvanic cells and how this works in this chapter. But for now, just know that one type of device, right? Remember, an electrochemical cell is that device where this conversion occurs. One type is called a galvanic cell, and that's the one where chemical energy is creating our electric energy. Our second one is an electrolytic cell. And in this one, we're actually going to use an electric current to drive a non-spontaneous chemical reaction. Remember, non-spontaneous chemical reactions need an external influence to occur. That external influence in this case is that electric current. So an electric current drives a non-spontaneous chemical reaction. So again, that electric current is that outside influence that's causing that non-spontaneous reaction to occur. Again, I didn't write this down, but my electrochemical cell, this is the device in which the conversion occurs. And when I say the conversion, I'm talking about this, right? The conversion between chemical and electrical energy. And these two are the opposite of each other, right? Galvanic cell, I have chemical generating electrical energy. Electrolytic cell, I have electric energy generating chemical energy, right? Driving that reaction. The type of reaction that we're going to see are going to be oxidation reduction reactions. So the bulk of this video is actually just going to be an oxidation reduction review, and then we'll also look at balancing oxidation reduction reactions. So oxidation reduction These you would have talked about in 150 or 151 in chapter 7. So you would have talked about solubility rules, right? You would have had precipitation reactions, acid-base neutralization reactions, and then also oxidation reduction. And remember, our oxidation reduction reactions were ones where we had the movement of electrons, right? If something's oxidized, it's going to lose electrons. If I have something that's reduced, it's going to gain electrons. Again, remember, we're talking about electric current here, and that's the flow of electrons. So if we can have our oxidation half reaction in a separate container than our reduction half reaction, the electrons lost from this have to move to here, and if we have that move across a wire, we have electric current. So the reactions that we're going to see in this chapter are all going to be oxidation reduction reactions. So again, oxidation, this is the loss of electrons. Could be one, could be more than one, but it's losing electrons. We are going to assign oxidation numbers, and our oxidation number becomes more positive, right? Because it's losing electrons. Remember, electrons are negatively charged. So if it's lost negative charge, it's become more positive. And then again, be careful. I'm not saying it becomes positively charged. I'm saying it becomes more positive. So if it went from a -3 to a -2, right? -2 is more positive than -3 is. It's lost electrons. It's been oxidized. Our reduction here, we're going to gain electrons. Be really careful, right? We see the word reduction, it's really easy to think loss, but remember what we're gaining is negative charge. So the gain, it's not worded very well, but it's gaining electrons. And if we look at oxidation numbers, it's going to become more negative, right? My oxidation number is going to be smaller. It is gaining electrons. So oxidation is the loss of electrons. Reduction, we're gaining electrons. There's a couple different mnemonics for remembering this. The one that I learned, and this is back in the day when we had overhead projectors, but my instructor had a big overhead projector of a lion. This is a lion, believe it or not. An artist I will never claim to be. So we have a lion, his name's Leo, and Leo says grr. So the L is lose, the E is electrons, and then oxidized. Just hard to spell vertically. So lose electrons, oxidize, and then gain electrons, reduced. Of course, sometimes it's easier to just remember it than try to remember a mnemonic, right? If we're oxidizing, we're losing electrons. If we're reducing, we're gaining electrons, which makes sense, right? If you're gaining electrons, you're becoming more negative, so reduction. If you want a way to remember it, beautiful picture of a lion here. His name is Leo, and he says grr. An example for us. We will have zinc solid. I'm going to react it with copper 2+. I'm going to produce zinc ions and copper solid. And this is just a net ionic equation. Remember, you can't have cations without an accompanying anion, but those have all been crossed out. I just want a very simple one for us to start. And I'm just going to look at charge. We will talk about oxidation number here shortly. But if I look at zinc, it's going from 0 to 2+. And when we do oxidation number rules, you're going to learn that if it's just an element, right, something in its elemental form, which zinc is here, its oxidation number is 0. And then if you have a monoatomic ion, so just a single atom with a charge, which is what zinc is, its oxidation number is the same as its charge. And I will write those down shortly, but this is going to be 0 and this is going to be +2. Do note, and I'll say this a couple times, when we write charge, it's standard to write the number and then the sign, so +2 is the charge. When you write the oxidation number, you actually write the charge, or not the charge, but the plus or minus first, and then the number. So 2 plus is the charge, +2 is the oxidation number. And that's how we know the difference. It's standard that if the sign comes first and then the number is the oxidation number, the other way around is the charge. Either way, it became more positive. It became more positive, it lost electrons. And if it's lost electrons, it's oxidized. So zinc is being oxidized. If I look at copper, copper is going from +2. Just wanted to be somewhat consistent with my colors here. I'm forming copper solid. Again, if it's in its elemental form, its oxidation number is 0. If it's a monoatomic ion, so a single atom with a charge, its oxidation number is numerically the same as its charge. When we write it that way, I'm going to switch the position of that number in that sign. So here I'm going from a +2 to a 0. It's becoming more negative because it gained electrons. And if it gained electrons, it is reduced. So copper is being reduced, zinc is being oxidized. The electrons that zinc are losing are being given to copper 2+, right? I have one type of atom losing electrons, another one gaining them. We can also define what's called our oxidizing and reducing agent. And these terms can be kind of confusing at first, but you really just want to remember what this word agent means, right? If you're an agent for something, you're causing it to occur. So, right, if you're an agent for change, you're causing change. Here, this is an agent for oxidizing, right? So it's causing an oxidation. It's not being oxidized, it's causing something else to be oxidized. So the oxidizing agent causes another atom to be oxidized. Right? Means it's causing another atom to lose electrons by gaining electrons itself. Right? Oxidation reduction reactions are always going to occur together, right? Something can't gain them if something else doesn't first lose them. It's not just pulling them out of nowhere, right? Something has to lose them for something else to gain them. And if something is going to lose them, they're not going to just disappear. Something else has to take them. So they're always going to occur together. So my oxidizing agent is actually gaining electrons. It's being reduced. And because it's gaining them, it's making someone else lose them, or another atom lose them. So it's causing something else to be oxidized by taking electrons itself. So the oxidizing agent is the atom, or is the reagent that contains the atom that is being reduced. And then the reducing agent, just the opposite. Right? It's the agent for reduction. It's not being reduced, it's causing a reduction. So causes another atom to be reduced, right? It's the agent for reduction. By losing electrons itself. So the reducing agent contains the atom that's being oxidized, which means it's forcing something else to take those electrons, right? Is the agent for a reduction. And for this one, because I'm not giving us the entire compound, I'm just actually giving us the atoms, right? Because zinc here is what's being oxidized, zinc is going to be my reducing agent. And because copper 2 plus is what's being reduced, it's going to be my oxidizing agent. So it's just going to be Zn and then Cu plus for those. I'm going to write those in these examples. So my oxidizing agent, I think I might have said it backwards, are these two. If I had the entire compound, like instead of copper 2 plus, if I had copper sulfate, you would write copper sulfate down as the oxidizing agent. It would be the entire compound, not just the atom. When you're picking what's being oxidized or reduced, you do just pick that atom. And we'll do some more examples where it's a little more complicated and easier to see that. Before I do more complicated examples though, I do want to go through our oxidation number rules. So rules for assigning oxidation numbers. So our first rule, an atom in its elemental form has an oxidation number of 0. So just be careful, right? Not everything's elemental form is just a straight up atom, right? Zinc here is one of our examples that we just did. That is its elemental form, so its oxidation number would be 0, right? It's a solid at room temperature. If I was to look at bromine, however, bromine exists in nature as a diatomic molecule. It's a liquid, and its oxidation number here is still going to be 0 because that is its elemental form. So essentially watch out for the diatomic ones, right? This is its elemental form. If I had hydrogen, H2, that's its elemental form, so its oxidation number is going to be 0. If I had sodium, solid, its oxidation number is going to be 0 because that is its elemental form. So just essentially a straight up atom, right? Just remember that our diatomic molecules exist as 2 of them in nature. So if you see that, its oxidation number is going to be 0. Right, just a quick review, our diatomic elements. These are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. So if you see any of those just in that form, its oxidation number is going to be 0. So elemental form, 0. Our second rule, the oxidation number on a monoatomic ion. So we mentioned this a little bit earlier, but it just means a single atom with a charge. So not a polyatomic ion, right? Poly means more than one atom. Here it's a single, mono means one, a single atom with a charge. So Na+. So the oxidation number on a monoatomic ion is the same as its charge. So examples, sodium plus, oxygen 2 minus, let's do aluminum 3 plus, fluorine minus, right? So sodium, it's a single atom with a charge. Its oxidation number is going to be +1 because its charge is +1. Oxygen 2 minus, so its oxidation number is going to be a -2. Again, remember when we're writing oxidation numbers, sign first, then the number. Plus 3, 3 plus is the charge, minus 1. So those, the ones in purple there, would be my oxidation numbers. I didn't define oxidation number, and maybe I should up here, but essentially what our oxidation number is, it's the effective charge. So we're going to give oxidation numbers to things that don't have charges. Like water is covalently bonded, right? If I have a water molecule, it doesn't have any charge. There's no formal charge, there's no net charge. I don't have ions, but we're going to give it charge anyway. So it's the effective charge when bonding electrons are assigned to the electronegative atoms. And I wouldn't even really worry so much about this last part. I would just think effective charge. Kind of, if it had a charge, what would its charge be? Even though it's not charge. A lot of times in lower level chemistry classes like 130, they'll just tell you that the oxidation number is the same as its charge. That is not true. It's true, right, if it's a monoatomic ion, but again, if I have water, water doesn't have a charge, so it's not a true statement. So kind of, if you were to look at the bonding electrons, what would its effective charge be? So our third rule, because we're going to start getting into covalently bonded compounds next, is that the sum of oxidation numbers must equal the net charge. And you might want to add here, sorry, the sum of oxidation numbers on all atoms in a molecule or polyatomic ion. Sorry to add the big thing there, but the sum of all oxidation numbers on all atoms in a molecule or polyatomic ion must equal the net charge on that molecule or polyatomic ion. So again, if I look at water, right? Water, I have oxygen bonded to 2 hydrogens. And what we're going to do is we're going to give oxygen an oxidation number, and we're going to give each hydrogen an oxidation number. And then the sum of those 3 oxidation numbers has to equal 0 because the net charge on water is 0. If I was to look at ammonium, ammonium is NH4 plus. We're going to give oxidation numbers to nitrogen and each of the hydrogen. So I'm going to essentially have 5 oxidation numbers, right? 1 here, 1 here, 1 here, 1 here, 1 here. And then the sum of those, if I add them together, is going to equal a +1 because that's the net charge on that polyatomic ion. So we're going to assign oxidation numbers to all the atoms in our molecule or polyatomic ion. And then when we total them together, they have to equal the net charge. So if the net charge is 0, they have to sum to 0. Here I have a net charge of a +1, so they have to sum to +1. Right? If I was to look at sulfate, this time I'm going to have 5 oxidation numbers. So I have 4 oxygens, they each get 1. Sulfur gets 1. And then when I add them all together, they have to sum to a -2 because that's the net charge on that polyatomic ion. So rule 4, the oxidation number on an atom in a compound, let's say in a molecule. Remember, molecules are covalently bonded compounds, or a polyatomic ion. The bonds between the atoms in a polyatomic ion are covalent. So again, looking at ammonium here, ammonium has 4 bonds between nitrogen and hydrogen, and all 4 of those bonds are covalent. The bond between ammonium and chloride would be ionic, right? Because it's between charged atoms, right? Charged particles, I should say. But these bonds within the polyatomic ion itself are covalently bonded. So the oxidation number on an atom in a molecular polyatomic ion is often, not always, this is going to be important because a lot of times it's not even close, the same as if it were a monoatomic ion. So kind of we go back up and look at water here. Oxygen doesn't have a charge, but if it did, it would be -2. So the oxidation number is often -2. So I'm going to have some sub rules under number 4. Our first one's hydrogen. Hydrogen has an oxidation number of +1 when bonded to a nonmetal, and -1 when bonded to a metal. In this last part, -1 when bonded to a metal, you don't even really need that, right? Because that's actually covered, if we go back up, by rule number 2, right? Remember, hydrogen's a non-metal, so if I was to write sodium hydride, right, Na+, this is an ionic compound. It's Na+ and H-, so my oxidation number on sodium is a +1 because its charge is +1, and that's rule number 2, and then hydride is a -1, its charge is -1. So if it's bonded to a metal, it's actually an ionic bond, and its oxidation number is the same as its charge. So that second statement again, or the second part of that statement, is actually rule number 2. We'll come back and do an example of the other one after I give us our next rule, which is oxygen. We'll use water here as our example. So oxygen usually has an oxidation number of -2 unless it's in a peroxide. Remember, a peroxide was a polyatomic ion that you needed to memorize, and it was O2 with a -2 charge. It was on the list of ones to memorize from 150, 151. So if it's in a peroxide, we can actually look at this, right? I have my 2 oxygens bonded to each other. It has a net charge of -2. If we go back up to rule number 3, right? We know that when we add the oxidation numbers for the 2 oxygens together, they have to equal the net charge. So when I add the oxidation number for this oxygen to the oxidation number for this oxygen, it has to equal a -2. So that means that each oxidation, or each oxygen, has to be a -1. So oxygen usually has an oxidation number of -2 unless it's in a peroxide. And then it is -1. And I'm just going to move this up here. Or when it's bonded to fluorine, and then it's +2. So scrolling back up, I'll come back so you can copy that, I promise. But if we go back up to our definition here, the part that I said you didn't have to really focus on so much, we said our bonding electrons are assigned to the more electronegative atoms. What that essentially means is the more electronegative atom in my molecule is generally going to be the negative one when it comes to oxidation numbers. So the only atom that we have that's more electronegative than oxygen is fluorine. So if oxygen's bonded to fluorine, fluorine is going to have the negative oxidation number, and then oxygen is going to become positive. So a couple examples for this one. And we do have a part C also, but if I was to look at water, right? Here, hydrogen is bonded to a nonmetal, so +1 for its oxidation number. And then oxygen, right? The sum of my oxidation numbers have to be 0, so I have a +1. Actually, I want to write these in a different color just so they stick out more. So +1 and a +1 gives me +2, which means oxygen would have to be a -2. You could also use this rule for oxygen, right? Oxidation number is going to be -2 unless it's in a peroxide, which it's not, or bonded to fluorine, which is not, so -2. And then again, a -2 and 2 positive 1s equals 0. That's what it should equal. If I was to look at oxygen bonded to 2 fluorines, so F2O, this time oxygen is going to be a +2 and each fluorine is a -1. Again, they sum to 0 because the net charge on F2O, or OF2, however you want to do it, is 0. But again, fluorine is going to be the -1, oxygen becomes positive. Rule C, and this is for halogens, and this is always worded kind of weird, but halogens often have an oxidation number of -1 unless they are bonded to oxygen unless that halogen is fluorine. So essentially we have an exception to the exception, right? Halogens usually have an oxidation number of -1 unless they're bonded to oxygen. If that halogen happens to be fluorine though, fluorine's still -1. So just basically remember fluorine will always be -1. Right? If I go back up and look at this example, fluorine's bonded to oxygen, fluorine's going to be -1. If I was to do a similar example, but change those halogens to chlorine, now oxygen is going to stay -2, and then I have to figure out what the chlorines are. Again, remember I have 2 of them. It has to sum to 0 because I have no net charge. So each one of these chlorines is going to be a +1. So halogens are usually going to be -1 unless they're bonded to oxygen. And I can't say then they're blank because you have to figure it out. It could be different. If I was to bond 3 chlorines to oxygen, they're going to have a different oxidation number. So usually -1 unless they're bonded to oxygen. And then the exception to that exception is that if the halogen's fluorine, this is always going to be -1. Basically, fluorine's the most electronegative one. It's always going to get to be negative. Halogens are usually more electronegative, but oxygen is more electronegative than all of the halogens except for fluorine. So oxygen gets to stay negative and my halogens become positive. That is our reasoning. So I just want to do a couple more examples. Actually, let's do an entire reaction, and then we'll do the examples as kind of part of our reaction here. So this one's going to be kind of big. I'm going to have 11 protons, so H+, plus 2 MnO4 minus, those are aqueous, plus 5 chlorines, and I didn't leave myself enough room, plus 2 manganese 2 plus 5 HClOs, and 3 water. So I didn't quite fit all those in there. So what we're going to do is we're going to assign oxidation numbers to all of our atoms. We're going to determine what's being oxidized, what's being reduced, which is the oxidizing agent, and which is the reducing agent. So I'm going to go through here. So H plus, and I'm going to ignore the number that I have. We are going to balance oxidation reduction reactions in this chapter. This one is balanced already. I know it looks kind of messy, but I'm just going to ignore these numbers for now. So I'm just going to look at hydrogen. I don't care that there's 11 of them. So hydrogen here has a +1 charge. It's a monoatomic ion. So its oxidation number is going to be the same as its charge. I'm just putting the sign first. Here again, I'm going to ignore this 2. I know that oxygen is going to have an oxidation number of -2 unless it's in a peroxide, which is not, or bonded to fluorine, which it's not. So oxygen is a -2. I happen to have 4 of them. Let me just rewrite MnO4- down here just so we kind of have it out of the way. I know that each oxygen is -2 and I have 4 of them, so that gives me a -8 total for the oxygens. I know that when I add the oxidation number for manganese to it, it has to sum to a -1, right? Because that's rule number 3. So I know that manganese has to be a +7, right? A +7 and a -8 is going to give me that -1. So manganese here is going to have a +7 for its oxidation number. Cl-, this one's easy, monoatomic ion, -1. Same with this next one, monoatomic ion, +2. Let's rewrite hypochlorous acid down here. And what I would do for this one, and you can do it however you want, but I would dissociate these. I know that it's H plus and ClO-. And if you don't see that, you could still, we can do it both ways if you want. I know that hydrogen here is +1 because I'm looking at it as a monoatomic ion. If you wanted to do it here and just think covalent bond, which it is, I just dissociated it because I know it's an acid and I know it's an aqueous solution. And we just spent over a month on acids and bases, so we know that it is dissociated. But if you want to keep it together, hydrogen's bonded to chlorine, which is a non-metal, so +1. Oxygen, -2, unless it's in a peroxide, which is not, or bonded to fluorine, which is not. My halogen then is bonded to chlorine, so we just have to figure it out. I know that when I add my oxidation number to chlorine to my oxidation number for oxygen, it has to sum to a -1. So that means chlorine is going to have to be a +1 also. If you would have done it here where you just think of them as being together, oxygen again is a -2 because it's not in a peroxide, it's not bonded to fluorine. And then I know that the sum on this has to be 0, right? Because it doesn't have a charge, which means chlorine has to be a +1 because +1 and +1 and -2 is equal to 0. So +1 for oxygen, +1 for chlorine, -2 for oxygen. And then water, we already did that one, so I'm just going to write them on here. -2 for oxygen, and then a +1 for each hydrogen, right? There are 2 of them, but each one is +1, right? +1, +1, and my -2. So those are my oxidation numbers. I'm going to get this stuff out of the way now. So we want, again, our atom that's going to be oxidized. We want our atom reduced. When picking what's being oxidized and reduced, you're always just going to pick an atom. And then we're also going to pick our oxidizing agent. Here we're going to pick the entire compound, if it is a compound, and our reducing agent. So what we're going to do is we're going to look at the oxidation numbers that have changed. Not all of them have changed, right? If I look at hydrogen over here, it's a +1. And if I look at hydrogen here, it's a +1. And here it's a +1 also. So it didn't gain electrons, it didn't lose electrons, it was neither oxidized or reduced. If I look at oxygen, here it's a -2. Here it's a -2, here it's a -2. Again, it didn't change, so it wasn't oxidized, it wasn't reduced. We're only, again, going to look at the ones that change. So if I was to look at manganese, here it's a +7, here it's a +2, right? So I went from +7 to +2, right? It was reduced, it gained electrons. So the atom that's being reduced is manganese. The other one that changed, and I'm just going to get this out of my way here, is chlorine. Chlorine went from a -1 to a +1. So it became more positive, right? It lost electrons. So the atom that's oxidized is chlorine. And then remember, the one that's oxidized is causing something else to be reduced. So it's the reducing agent. And then again, remember here, you're writing the entire thing. And it's always going to be on the reactant side, right? The products are the products of the oxidation and reduction. They're not losing electrons or gaining electrons. They have already gained or already lost, right? They're not causing something to occur. They're what happens after it has occurred. So for all of these, always, always, always only pick reactants, never pick products. So what I'm going to do for this one is I'm going to find chlorine. Cl- then is what I'm going to write down. My oxidizing agent, right, the atom that's gaining electrons is going to cause something else to lose them. So my oxidizing agent is going to contain the atom that's reduced. The atom that's reduced is manganese. And again, I'm going to pick the whole compound. In this case, it's a polyatomic ion. With chlorine, it was actually a monoatomic ion. But you're picking like the entire thing just as it's written on the reactant side. Again, always pick reactants. So assign oxidation numbers using our rules. If it hasn't changed, it's not undergoing an oxidation or a reduction, right? It hasn't gained or lost electrons. Just look at the ones that changed. If it's becoming more positive, it lost electrons. If it's becoming more negative, it gained them.